Precipitation is merely another way of looking at solubility equilibrium. Basically, if you pass the saturation point, you will get a precipitate. Rather than considering how much of a substance will dissolve, we ask ourselves the question, will a precipitation occur for a given starting ion concentration? Basically, if I have X concentration of cation and Y concentration of anion, will I be past the saturation point and cause the precipitation to occur? To determine whether an equilibrium system will go in the forward or reverse direction requires that we evaluate the reaction quotient Q. This is very similar to what we did in the past to calculate Q. It is exactly the same as the K expression, except you put in an initial concentration so you're not sure if you're at equilibrium or not, or if you have the saturation concentration values. Now, some books will refer to this as IP or P. I'm going to refer to it still as Q to keep it the same way as we've done in the past. To predict the direction of reaction, you compare that Q to the KSP. The reaction quotient has the same form as that KSP expression, but the concentration of the products are starting values, not necessarily saturation concentrations. And there are any values that we're plugging in there and trying to determine if that Q is equal to that KSP. If we're at the KSP value, then we're at the saturation point. If it's less than the KSP, then we're before the saturation point. If the Q is greater than KSP, we're past the saturation point. Consider the following equilibrium. Lead 2 chloride breaks up into lead 2 and 2 chloride ions. We can set up the KSP for this expression as we've done before. It'd be the concentration of your lead ions to the first power times the concentration of your chloride ions to the second power, accounting for that coefficient. And these are equilibrium values, meaning that I have saturated amounts of lead and chloride in solution. When I multiply them, I get the KSP value. Now, I may have some initial concentration of lead and some initial concentration of chloride. If I plug it in the exact same type of calculation, I get something what we refer to as Q, because we're plugging in initial concentrations, not necessarily equilibrium concentrations or saturated concentrations. If they happen to be the saturated concentrations, then that Q will be equal to that KSP and we'll be at that saturation point. But if that Q does not equal K, then we can make decisions about if we have a precipitate or not based on the size of that Q to the KSP. If Q is equal to KSP, then what we're saying is we're at the saturation point. The solution is just saturated with ions, and any additional solid that we would add would not dissolve in solution, but instead precipitate out. So we have a saturated solution. We're just at that point where a precipitate would form. If I add any more, that precipitation will occur. If Q is less than KSP, the solution is unsaturated and more solid can be dissolved in that solution. In other words, there's no precipitation form. Now, we can use our same analogy as before with writing our reactions to determine what's happening with the Q value to see which way it's going to shift to see what's going to happen. Let's look at it. If Q is less than KSP, that means I need my Q to get greater to reach that saturation point. So that means that I need the Q to increase in value. Well, looking at your equilibrium here, solids going to ions, the Q would be the concentration of your ions as your equation. Well, for Q to get bigger, then my concentration of my ions has to get bigger. Well, for that to happen in my equilibrium, that would mean that my reaction would have to shift to the right, which means it's pointing toward making more ions, which means I have more room for more substance to dissolve. So in a case where Q is less than KSP, we're talking about no precipitation. Basically, we're before the saturation point. Now, you can either memorize it that Q is less than K means no precipitate before the saturation point, or you can figure it out like we did here. Now, one word of caution here, we're figuring it out. It's not really shifting to the right. We're just using the same analogy to make our determination. If Q is greater than KSP, okay, The solution is supersaturated, meaning the solution contains a higher concentration of ions than possible at equilibrium, which basically means a precipitated form. Now, using the same philosophy, I can look at the reaction and see which way it's going to shift to see if I'm going to have a precipitate or not. So I can say, okay, Q is greater than KSP. That way I need Q to get smaller to reach that equilibrium, which means my concentration, my ions have to get smaller, which means for this reaction to happen, okay, means for the ions to get smaller, it's going to have to shift to the left, which means it's pointing to solid, which means it's going to have a precipitate. So if we're talking about Q is greater than KSP, then we're talking about a precipitate will form because we're after the saturation point. So you can either memorize it or figure it out, but I just want to caution you that in reality it's not really shifting one way or the other, okay? But I'm using this to tell you to figure out which way it lies if you're trying to understand and predict which way it's going to go. So your choice is to understand it, or number two is to just memorize it. Q less than KSP, no precipitate. Q greater than KSP, precipitate. Let's look at an example. The concentration of calcium ion in blood plasma is 0.0025 molarity. If the concentration of oxalate ion is 1.0 times 10 to the negative fifth molarity, do you expect calcium oxalate to precipitate? KSP for calcium oxalate is 2.3 times 10 to the negative ninth. So I'm trying to decide if precipitate's going to form or not, so I need to figure out my Q, compare that to KSP to decide. So the first thing I'm going to have to do is write my equilibrium. So let's write the equilibrium for calcium oxalate. Once calcium oxalate breaks up into calcium ion and oxalate ions. In this problem, it gave me my concentrations, concentration of calcium and the concentration of my oxalate ion. So I know I have 0.0025 molarity of calcium and 1.0 times 10 to the negative fifth molarity of oxalate ions. Now that's all I have in the problem. So even though this reaction is a 1-to-1 ratio, okay, if there was some coefficients in front of calcium or oxalate, I wouldn't account for them here because I'm giving the amount of calcium and the amount of oxalate in the problem. That relationship is only when I'm trying to relate back to the molar solubility of that substance. So then I have to write the Q for this expression, which would be the concentration of calcium to the first power times the concentration of my oxalate to the first power. Then I'll plug in those concentrations, which gives me Q is equal to 0.0025 times 1.0 times 10 to the negative fifth, which is Q is equal to 2.5 times 10 to the negative 8. So now I have to take this Q and compare it to KSP. I see that Q is 2.5 times 10 to the negative 8. KSP is 2.3 times 10 to the negative ninth. 10 to the negative 8th is larger than 10 to the negative 9th. Therefore, my Q is greater than KSP. This means that I'm past the saturation point, which means that there will be a precipitate formed. So there will be a precipitate formed. Let's look at this one. The concentration of lead ion is 0.25 molarity. If the concentration of chloride ion is 0.0060 molarity, do you expect lead chloride to precipitate? And I give you the KSP for lead chloride. Once again, I'm going to have to write my expression first, which is lead 2 chloride goes into lead ions and chloride ions, 2 of them. In this problem, they told me the amount of lead I had and the amount of chloride ions. So I know I got 0.25 molarity of lead and 0.0060 molarity of chloride. Once again, that is all the concentration of lead and all the concentration of chloride I have, so I am not going to account for that 2-to-1. Basically, that 2-to-1 is just telling me that I'm going to take some part of that 0.25, one part of that, and 2 parts of that 0.060, combine it to form my lead 2 chloride. That's just my ratio. My pool of stuff is I have 0.25 and I have 0.060. That's all I have. I can't double it just because I need a 1-to-2 ratio. It's an important concept, something to remember. If you were to account for that 2 in this problem, you'll get the wrong answer. Okay, so got to read the problem of what I have. If I'm coming from the molar solubility of the substance, then I got to account for it. If I'm not coming from the molar solubility, then I do not. So I'll set up my Q. Q is equal to my lead 2 ion concentration times my chloride ion concentration squared. Plug in those values, which gets me Q is equal to 0.25 times 0.0060 squared, which gives me Q is equal to 9.0 times 10 to the negative 6. Next step, compare that to KSP. And we find that Q at 9.0 times 10 to the negative 6 is less than 1.7 times 10 to the negative 5th. Therefore, since that's the case, we are basically below the saturation point, okay, which means that there is no precipitate being formed. So no precipitate. If you were to count and did double that chloride concentration, you would get the opposite answer, which is the wrong answer. Okay, so it's an important concept, okay, of realizing more concentration you have and when you double it and when you don't double it. Let's look at now how we would use this precipitate, no precipitate in a mixture problem. A student mixes 0.200 liters of 0.0060 molarity of strontium nitrate with 0.1 liters of 0.015 molarity of potassium chromate to give a final volume of 0.3. Will a precipitate form under these conditions? Give you the KSP of strontium chromate. Well, the first thing we're going to do is write a reaction and based on solubility rules decide if there's a possibility that a solid could form or not. So you write your reaction, you get strontium nitrate plus potassium chromate, gives me strontium chromate plus potassium nitrate, balance the charges and balance the whole equation, end up getting a 2 in front of the potassium nitrate. By solubility rules, strontium chromate is a solid and potassium nitrate is an aqueous solution. All nitrates are soluble. So the question is, do we have enough strontium coming over and enough chromate coming over to be past that saturation point and cause a precipitate to happen? Now, a clue that you have which species is going to be an insoluble salt and form would be that they give you the KSP of something. So you need to be able to write a balanced equation and know what the precipitate is based on solubility, but you're also given a hint here based on that KSP given to you of that substance. Okay, so how am I going to figure out how much strontium I have and how much chromate is? Well, I got to go back and look at, where all the strontium is coming from in this problem. Well, all the strontium is coming from strontium nitrate. Okay, so I can take that volume and that molarity and figure out how much strontium nitrate is present. Now, what is the relationship between strontium nitrate and strontium? Well, there's one strontium for every strontium nitrate, so it's a 1-to-1. So if I calculate the strontium nitrate concentration after the dilution, then I also have my strontium concentration. Now, what if I needed the concentration of nitrate? Well, there's 2 nitrates for every strontium nitrate, so I would have to double it. Okay, 1-to-2 mole ratio. Okay, for every 1 strontium nitrate, you got 2 nitrate ions in the numerator, 1 strontium nitrate in the denominator. It cancels out, multiply by 2. So, strontium ion concentration, which is equivalent to the concentration of my strontium nitrate. Okay. We'll take the 0.2 liters times the 0.006 molarity divided by the 0.3 liters, which gets me 0.0040 molarity. As I said, if I wanted the nitrate concentration, since it's a 1-to-2 ratio, I'd have to double it. How would I figure out the chromate? Okay, well, that's going to come all from that potassium chromate. Okay, it's coming all from that potassium chromate. And what's the ratio between chromate and potassium chromate? 1-to-1 again. Okay, so if I can figure out the concentration of my chromate, it's the same thing as the concentration of my potassium chromate. Okay, now if I wanted the concentration of potassium, since there's 2 potassiums for every 1 potassium chromate, it'll be double the value. Okay, to calculate it, it'd be 0.1 liters times my 0.015 molarity divided by my 0.3 liters, which gets me 0.0050 molarity. So now I have my concentration of strontium and my concentration of chromate. I need to find out if I have enough of both of them to reach past that saturation point and cause precipitation. Now to determine that, we'll be doing my Q. So I'll now write my reaction of that insoluble salt. Strontium chromate breaks up into strontium ions and chromate ions. I was given the concentrations in that by calculating it. So I got 0.004 molarity of strontium and 0.005 molarity of my chromate. Write my Q expression, which is my Q is equal to my strontium 2 to the first power, chromate to the first power, equal to 0.0040 times 0.0050, which gets me 2.0 times 10 to the negative fifth. I'll now need to compare that to KSP. And I find that 2.0 times 10 to the negative fifth is smaller than my KSP, which is 3.6 times 10 to the negative fifth, not by a lot, barely, okay, indicating there would be no precipitate because I'm below the saturation point. I'm just below the saturation point, not by a large amount, but no precipitate because I'm below the saturation point. Okay, that can take much more strontium or much more chromate to get precipitation to occur, but I'm below it. Well, since I'm below the saturation point, my equation really to be correct, I would take that solid and convert it to aqueous because I'm below the saturation point. Therefore, there would be no precipitate formed in the problem the way it's posed in this case. Homework 43. Okay, homework 43 deals with questions about precipitation. Okay, that's the last homework assignment that we'll be assigning for this next test. However, there's some other concepts that we're going to cover that we'll have no direct homework questions about, but you are responsible for the concepts that we're going to cover in the next few slides. So we'll continue on this homework set with this information. We're going to talk about now selective precipitation. Selective precipitation is a technique of separating two or more ions from a solution by adding a reactant that precipitates first one ion, then another, and so on and so forth. Basically, we selectively add a component to elute cations or anions one at a time based on solubility. Example. I could slowly add potassium chromate to a solution containing barium and strontium. Well, barium chromate precipitates first due to its lower solubility than strontium chromate. So I can add potassium chromate, and what's going to happen is the barium chromate will precipitate out first. Okay, I can get most of that out, separate the solid from the liquid, continue to add potassium chromate, and then what's going to happen is the strontium chromate will come out second. So I can use selective precipitation to basically get one ion out and then get the second one. After most of the barium ion has precipitated, strontium chromate will begin to precipitate out. It is therefore possible to separate the barium from the strontium by selective precipitation using potassium chromate. We take advantage of this in qualitative, quantitative type analysis. Most of the time there's an experiment dealing in Gen Chem 1 or Gen Chem 2 which deals with qualitative analysis where we take advantage of this selective precipitation. Basically what you have is typically some solution, okay, that has maybe several metals in it of some type, and then we add some reagent to that solution. And what's going to happen is some of those metals will form solids, basically precipitate out, and some of them will stay in solution, which basically mean there'll be aqueous ions. Okay? Well, next what we can do is take that solid and you add another reagent to it. And once again, same thing. Some of those metals will then form solids, and some will form aqueous ions. The aqueous ions, same thing. You can add some reagent to it. And some will form solids. And some will form some aqueous ions. Right? So basically, there's a chain going on. You got a solution, you add something, you get some ions, some metals to form solids, you get some other ones being aqueous, and you do the same thing again with different reagents. So you're selectively getting things to precipitate by what you're adding to it. Okay, so you figure out what's there. Now, to decide if something will precipitate first or not, we need to be able to calculate the molar solubility of things. So let's look at that next. Okay, you can't just look at the KSP, you got to look at the whole picture. Okay, so let's look at this. Comparing solubilities. Which one is more soluble in water? I'm trying to figure out which one's going to precipitate out first. I want to look at this and figure out which one's going to be more soluble. Now, typically, okay, when we're talking about acids and bases, I could look at the Ka or Kb and decide which one's going to be a stronger acid by the size of the Ka. The larger the Ka, the stronger the acid, etc. Now, I can't just look at KSPs and decide that because I got to compare apples and apples. Okay, what do I mean by that? Well, you look at calcium carbonate, okay, there's 2 ions there, okay? If you look at silver bromide, there's 2 ions. If I look at calcium fluoride, there's calcium, and then there's 2 fluoride ions, so they're basically 3 ions. Okay, that's accounted for when you calculate your molar solubility. So if I'm comparing apples and apples, I can just look at KSP. I can look at KSP of calcium carbonate as 3.8 times 10 to the negative 9th. And silver bromide, KSP is 5.0 times 10 to the negative 13. Well, since KSP is larger for calcium carbonate, I can say that's more soluble than silver bromide. But we're comparing apples and apples. What do I mean by that? Let's go ahead and calculate the molar solubilities so I can show you that we're comparing apples and apples. How would I calculate the molar solubility? Well, first I got to write my reaction. Okay, calcium carbonate gives me calcium plus carbonate ions. If I say the molar solubility of calcium carbonate is S, then that would mean that I have S calcium and S carbonate 1 to 1. And if I want to calculate the molar solubility, set up my KSP is equal to calcium concentration of calcium times carbonate concentration equal to S and S, plugging that into those values, which gets me 3.8 times 10 to the negative 9th KSP. Take the square root of both sides. Okay, which gives me my calculation of S then is equal to 6.2 times 10 to the negative 5th molarity. Do the same thing for the silver bromide. Okay, I have S molar solubility of silver bromide. That would mean that I have S silver and S bromide. Plug that into my KSP expression of my silver concentration times my bromide concentration, which is S times S, which is S squared. Once again, take the square root of both sides, which gets me S is equal to 7.1 times 10 to the negative 7th molarity. So, if I want to figure out which one of these is more soluble between the two, well, since the molar solubility of my calcium carbonate is larger than my molar solubility of silver bromide, which is 7.1 times 10 to the negative 7th, calcium carbonate will be more soluble compared to silver bromide. Now, I could have made that same decision by looking at the KSP, 10 to the minus 9th, compared to 10 to the minus 13th, because I'm looking at apples and apples. Look at the math here, okay? You're talking about S squared is equal to the KSP in both cases. So naturally, the one with the larger KSP is going to have the larger S. So therefore, I'm looking at KSP and can decide that the larger KSP will be the more soluble one. But let's see what happens when I do the third one that has 3 ions in it. You have a calcium and 2 fluoride ions. Let's see what happens in that case. If I have my molar solubility for calcium fluoride is S, then I have a case of S for calcium and 2S for fluoride. Plug that into my calculation. KSP is equal to the concentration of calcium times the concentration of fluoride squared, which is S, and 2S squared, with 2S squared would be 4S squared times S, which is 4S cubed, which then means I got to divide both sides by 4, okay, and then take the cube root of both sides, which then gets me an S equal to 2.0 times 10 to the minus 4th molarity, something we've already calculated a couple of times already. Now, if I want to compare everything and decide which one is the more soluble one, Well, then I would have to look at my molar solubility of these three. And the one with the largest number will be the most soluble one. So looking at these three numbers, which one's the larger one? Well, the solubility for the calcium fluoride. Therefore, it's going to be the one that's going to be case that is going to be the most soluble in water. Okay, so the most soluble in water in this case is calcium fluoride. Now notice the KSP is 10 to the minus 11th, which falls in between the other two KSPs, 10 to the minus 9th and 10 to the minus 13th. So it wasn't the one with the largest KSP was the most soluble. That's because we have to account for the ions. We had a different math involved here, which changes the molar solubility in your calculation. So you have to look at the molar solubility to determine which one's going to be the most soluble. Okay, so in this case, my calcium fluoride is my most soluble compound. Now, looking from the other side of the coin, if I want to say which one of these will be the least soluble and which one's going to precipitate out first, you would look for the one with the lowest molar solubility, which means then that my silver bromide is the one that's going to precipitate out first because of the lower solubility. So this is what you have to do to decide what's going to come out first and what I'm going to add to it to make something come out first. You're kind of looking at the solubilities of things and looking at the molar solubility and figuring out which one's going to have the least molar solubility, therefore it will precipitate out first. Now, sometimes it is necessary to account for other reactions that aqueous ions might undergo. For example, if an anion is the conjugate base of a weak acid, it will react with the hydronium ion. Hence, you got a neutralization. I have a base and I have an acid component. Therefore, there's going to be some reaction. So that can affect the solubility of a compound. So when I add an acid to an insoluble salt, I could make it be more soluble or less soluble depending on what's going on in that reaction. Okay, what species are we talking about? So you should expect the solubility to be affected by pH. By adding in complex and ions, you can affect the pH of the solution, which can affect the precipitation reaction. Okay, depending on what the substances are, by adding acid, I could get it more soluble, or it could be making it less soluble. It's a very complex problem when we're dealing with solubilities. Let's look at this one and see what's happening. I got calcium oxalate breaks up into calcium and oxalate ions. Okay, oxalate is a base. Okay, this is a base, right? So if I add some hydronium in the form of acid, what I'm going to get is a neutralization reaction. Okay, I'm going to have some neutralization reaction. So in that process of adding that hydronium, what's going to happen to the concentration of my oxalate? Well, because I'm adding that hydronium, then I'm going to have that neutralization reaction. My concentration of my oxalate is going to go down. So while that's going down, it's going to be affecting the concentration of my oxalate in my equilibrium. It's going less. Well, if I'm at equilibrium and now I'm pulling off some oxalate by reacting it with the hydronium, that acid I added, then which way is this reaction going to have to shift? You have to shift to the right. When it shifts to the right, that means that more of that solid is going to break up into ions. Okay, more of it's going to break up into ions, which means then the molar solubility of that calcium oxalate, it has to be going up or down. Which way? Well, if it's solid, it's breaking up into more ions. That means I'm getting more of that solid in the solution. That basically means that my solubility will be increasing, okay, by decreasing the pH. So in this particular example, my calcium oxalate, I can increase the solubility by increasing the pH. According to Lechartier's principle, as the oxalate ion is removed by the reaction with hydronium, more calcium oxalate will dissolve, thereby increasing the solubility. Therefore, you expect calcium oxalate to be more soluble in acidic solution, lower pH, than in pure water. The acidity will react with the oxalate and shift the equilibrium toward the right and allow more calcium oxalate to dissolve. Now, many metal sulfides are insoluble in water, but they dissolve in acidic solution. So one of these things, this is one of the things we take advantage of in qualitative analysis schemes. Qualitative analysis uses this change in solubility of the metal sulfides with pH to separate a mixture from metal ions. We add the H2S and adjust the pH of the solution, okay, hydrogen sulfide. By adjusting the pH in the aqueous solution of hydrogen sulfide, you adjust the sulfide concentration to precipitate the least soluble metal sulfides first. Okay, basically I can add this, separate it, get some of the metals to precipitate out and some not, separate them, do something else to the solid, take more of that aqueous, change it again, add some more H2S, change the concentration of sulfide again, get more of it, precipitate out, etc. So we can use this to our advantage to get qual scheme to work. Now, typically you do some type of qualitative experiment in the laboratory, okay? In the different freshman classes, typically there's some qualitative experiment that you tend to do. So, one thing I don't think I've done so far is define qualitative analysis, so let's go ahead and define it. Qualitative analysis involves the determination of the identity of substances present in a mixture. I want to know what's contained in that mixture. It could contain iron, copper, chloride ions, I don't care, whatever it is. I just want to know what's in there. That's qualitative analysis. Contrary to what we refer to as quantitative analysis, which is how much, okay? I want to know how much iron is there, how much chloride ion is there. So it's amount, quantity, okay? So qualitative is what's present. Quantitative is how much is present. In a qualitative analysis scheme for metal ions, a cation is usually detected by the presence of a characteristic precipitate. So we're going to add certain reagents to get certain metals to precipitate with certain characteristics. For example, I may add something in the form of red precipitate with iron. Okay, so if I add that substance and I get a red precipitate, I know iron's there. If I add that reagent and I don't get a red precipitate, I know iron's not present. Okay, so we can selectively see what's happening there by some characteristic precipitate. The next slide shows a figure that summarizes how metal ions in the aqueous solution are separated into 5 analytical groups. Now, these analytical groups have to do with solubility, not the groups on the periodic table. It's based on solubility. Here's the schematic. This is the entire schematic. If I had a mixture of metals and I wanted to figure out if I had any of the metals in that solution, I go through this whole large, elaborate scheme. Okay. Now, most experiments have like 8 to 10 metals in it, and you're only looking at a certain one of these groups. But we can just talk about this a little bit for you to get understanding what's going on in a qual scheme. You start off with a mixture of metal ions, okay? Could be several, could be all the metals, okay? And then we add HCl. Well, let's think about HCl. There's one of the rules in the solubility rules, okay? All chloride ions are soluble with the exception of lead, mercurous, and silver, okay? So if I add HCl, then the majority of my metals are going to stay as aqueous, okay? They're going to stay as aqueous ions. And just a couple of them, silver, mercurous, and lead, will form a solid. So I can separate my aqueous ions from my solid. Okay? Do a centrifuge of some sort and basically separate the solid. And if I get any solid, then I know that solid contains silver, mercurous, or lead, or a combination. Okay? It could have all 3 of them, and it could have only 1 in it. If I don't get any solid and I added HCl, that tells me what? I have no silver, mercurous, or lead. Okay? So that's my first step. Then I would take this group, this solid now, and I know I can heat it. And if I heat it, I know something about lead. Lead becomes more soluble as I heat it. So if I take this solid and heat it up, that lead solid would break up and form an aqueous solution of lead. I can separate that solution from the solid and then do other tests on that silver and mercurous to see if I got silver there or mercurous there. And if I let that solution that has possibility of lead in there, if I let it cool and there's lead, then what's going to happen? The precipitate's going to form. If I let it cool and there's no precipitate form, that means I have no lead. So there's certain tests that we're going to do after we get them broken down to solids and aqueous and continue on. Now, this aqueous ion now over here would now add some H2S to increase that sulfide concentration. And then what happens is these metals here form the sulfides, precipitates, and they precipitate out, while other metals will not, so they stay as aqueous. Then we continue on, add some more salt, change the sulfide concentration some more. Therefore, I can get more of these metals to precipitate out as sulfides. Also add a little bit of ammonia there to get the aluminum and chromium come out as the hydroxides. Okay. And then those ones that are still in solution, you continue on, add ammonia carbonate, okay, and get some of the metals to precipitate out as the carbonates or the phosphates, okay. And then we finally have our last group, which would just be potassium with sodium. Okay. So, got this elaborate scheme. You add in different reagents as you go, and you're making solids or not solids, and then continue to do tests along the way to see if you have metals. And if you get positive results along the way, you know you have those metals. If you have negative results, then you know you don't have those metals. Many metal ions, especially your transition metals, form coordinated covalent bonds with molecules or anions having a lone pair of electrons. Now, you may recall we talked about acid-base theories. We talked about Arrhenius. We talked about Bronsted-Lowry. Well, we also talked about Lewis. Okay, we're going to talk about Lewis again here because this type of bond formation essentially is a Lewis acid, which means it accepts a share of a pair of electrons, and the base, a Lewis base, makes available a share of a pair of electrons. For example, look at the silver ion can react with ammonia to form our diamine silver ion. Okay, I wrote this with the Lewis dot structures here. If you can see what happens, this ammonia is bringing over a lone pair with it. Okay, and silver has none. Since this is bringing the lone pair with it to form that bond, okay, then ammonia has to be my base, my Lewis base. Since silver is accepting that share of that lone pair, then this is a Lewis acid. Okay? And then it forms that complex. Now we can write this in a normal sense without the lone pairs, and you get silver plus two amines gives me my diamine silver complex. Now notice it has a double arrow. That means that we have an equilibrium again, which means there's a K associated with it. And we talk more about that K in a couple of slides. A complex ion is an ion formed from a metal ion with a Lewis base attached to it by a coordinated covalent bond. An example would be the one we just did. That's your diamine silver ion. Okay, that's a complex ion. Okay, it's a complex ion. It's a charged particle that has a coordinated covalent bond in it. A complex is defined as a compound containing complex ions. So you can have a complex as the cation in this case, and then an anion attached to it to make a compound. An example will be a diamine silver chloride. Okay, that whole diamine silver has a +1 charge. That's your cation, and then your chloride is your anion with a -1. So balance it out to 1 to 1 for the whole compound. A ligand is a Lewis base. It makes electron pairs available that bonds to the metal ion to form a complex ion. In this case, the Lewis acid is the cation, and then in ammonia, okay, is my ligand. Okay, we typically refer to that base as a ligand. Now, the aqueous silver ion forms a complex ion with ammonia in several steps. Okay, first off, you got silver 1 plus ammonia gives me my amine silver ion. Then that amine silver ion is not very stable, so then it reacts again with another ammonia to form the diamine silver ion, which is very stable. Okay, so in essence, you can see that intermediate cancels out, and the sum of this reaction is what we just wrote a few minutes ago. Your silver plus your two amines gives you your diamine silver ion. Okay, as we said, there is an equilibrium established, so there's a formation constant. So let's talk about what that K is. Formation constant Kf is the equilibrium constant for the formation of a complex ion from the aqueous metal ion in the ligands. Okay, so we can write a K the same way we've done it before. It would be your products over your reactants with solids and liquids 1. So in this case, the K would be your concentration of your diamine silver ion to the first power divided by your silver to the first power divided by your amine to the second power. Same way we set it up before. With, in this case, since we're talking about a formation constant, okay, we're going to give that a Kf. As before, this is unitless. Okay, there are no units. And also, it is temperature dependent. Okay, the same as the rest of the Ks. Okay, unitless and temperature dependent. This particular K has a value. It is 1.7 times 10 to the positive 7th. As we stated before, the larger that K is, the more stable that complex is. Since this is an extremely large K, this is a very stable complex. If I put silver and amine together, it very readily will form this complex because it has such a large Kf. Okay, very stable complex. large value means that the complex ion is quite stable. When a large amount of ammonia is added to a solution of silver, you expect most of the silver ion to react to form that complex ion. It has a large Kf, therefore the equilibrium lies far to the right. We handle these calculations the same way we did with any other K. Okay, we can work these calculations the same way we did previous problems. I want to bring up the dissociation constant, Kd. That's because when we do these reactions, you're going to have your reaction happen. It's going to form this complex, and then this complex will dissociate and form its ions. So to do the calculation, it seems more logical to do it as a dissociation, or at least in the sense that that's what we've done everything so far. So to keep everything the same, I'll do it as a dissociation. So let's talk about how you calculate Kd. Okay. Well, we take in that formation reaction and we flip it. And what did we talk about happening to a K if I flip a reaction? I got to do the reciprocal of that K. So I'll take that reaction we just talked about and flip it. So now I have my diamine silver ion forming silver ions and two amines. Okay. So I can set up my K for that, which would be my products over reactants, which means my reciprocal. Okay. I have concentration of silver times my concentration of my NH3 squared divided by my diamine silver ion. The actual value of that Kd then will be 1 over my Kf. As I said, this is important because if I do a calculation, I tend to do it as a dissociation, which I'll show you in a calculation. All right, what is the concentration of a silver ion in 1 liter of solution that is 0.1 molarity silver nitrate and 1 molarity ammonia? Kf is for the diamine silver ion is 1.7 times 10 to the 7. So we mix in silver nitrate and ammonia. Okay, that's going to have a reaction and it's going to form a complex. After that complex is formed, then we're going to have our equilibrium established and we want to know how much silver is there. Okay, so basically I want to know how much silver is going to be there after the complex is formed. Okay, so we're going to have to do this problem just like we did before with the neutralization reaction. I've got to figure out how many moles I got. Then I have to do my reaction, figure out new concentration, then do my equilibrium. Okay, same 4-step procedure. Since this is in liters, I'm not going to do millimoles. I'm going to do it in moles. So I'll calculate my moles initially. So I got to figure out how many moles of silver nitrate I had to start with. Okay, well I got 1 liter times 0.01 moles per liter, which means I got 0.01 moles. Ammonia, I got 1 liter. I got 1 mole per liter, which is 1 mole. Okay, next I got to write my reaction. So I write my reaction, which is silver nitrate plus 2 ammonias, gives me my diamine silver nitrate complex. Okay, next I got to figure out what's my limiting reagent. Okay. Well, I'm putting in 0.01 moles of silver nitrate and 1 mole of ammonia. Okay, I can't just take the smaller number because now I got a coefficient there. It's not 1-to-1 like the acid-base stuff. So I got to figure it out. I got 0.01 moles of silver nitrate, and the question is, what's my limiting reagent? So I can figure that out by saying, okay, well, how many moles of ammonia is going to take to consume up all that 0.01 moles of silver nitrate? Well, for every 1 mole of silver nitrate, I have 2 moles of ammonia needed, okay, to consume it up, which basically means I need 0.020 moles of ammonia to consume all 0.01 moles of my silver nitrate. Well, since I have 1 mole of my ammonia and I only need 0.02 moles of ammonia, okay, I only need 0.02 moles of ammonia. Is my ammonia in excess or limiting? Well, I got 1, I need 0.02, then I have an excess, a large excess of ammonia. So therefore my ammonia is in excess. and my silver nitrate is my limiting reagent. So I can set up my table now. And I have my moles initially. I got 0.01 for silver. I got 1 for ammonia, 0 for my complex. My change now is going to be my limiting reagent 1, which means I'm going to have a negative 0.01 moles of silver. And I have my change for my ammonia, but remember it's a 1-to-2 ratio, so it's a negative 0.02 moles. And I'm forming plus 0.01 moles of my complex. Add them up, I get 0 moles after reaction of silver nitrate, so I have no silver left from this reaction. That's why I want to figure out from the equilibrium how much silver is there. Got 0.98 for my ammonia, and I have 0.01 for my complex. Step 3 will be new concentrations of my ammonia and my ammonia complex. Okay, and that way I can do my dissociation. So your new concentration, my ammonia will be my 0.98 moles over 1 liter, which is 0.98 molarity. And for my diamine silver nitrate, which is a 1-to-1 to my complex, which my diamine silver complex is the same, which is 0.01 divided by 1 liter, which is 0.01 molarity. Next, I write my dissociation. Okay, I want to write it as a dissociation. So I have my diamine silver ion breaking up into my silver ion and my 2 ammonias. Do my table. Initially, I got 0.01 for my complex, 0 for silver, and 0.98 for my ammonia. My change is going to be negative on my reactant side and pluses on my product side. I need my mole to mole, my X factor, which is X for my diamine silver, X for my silver, and 2X, because I have that coefficient in front of the ammonia, for my change in my ammonia. Add them up, I get 0.010 minus X, X, and 0.98 plus 2X. Now I got to ask myself, how are these related? The way that we wrote this problem, we did it as a dissociation. That means these are all related through KD. So I'm going to have to change my KF to a KD, which means KD is equal to 1 over KF, which is 1 over 1.7 times 10 to the 7th, which is 5.9 times 10 to the negative 8, equal to my concentration of silver times my ammonia concentration squared divided by my complex, my diamine silver complex. Then plug in my values, my X, my 0.9 plus 2X, and my 0.01 minus X. Which gets me X 0.98 plus 2X squared divided by 0.01 minus X. Now I want to simplify the math. We're going to do it the same way we did before. I'll look at my concentration versus my KD. And if it's 3 powers of 10 or greater, then I'm okay, which it is in this case, which means then I can get rid of my 2X and my minus X, which means my math simplifies to 5.9 times 10 to the minus 8 equal to X times 0.98 squared. Don't forget, I got to square both terms, so I can't lose that square. I need to keep that square in it. 0.98 squared divided by 0.01, which gets me X is equal to 5.9 times 10 to the negative 8 times 0.01, meaning multiplying through by 0.01 and dividing through by 0.98 squared, which gets me 6.1 times 10 to the negative 10th molarity. What does X represent in our problem? It equals the concentration of our silver, which is our final answer. We're trying to find the concentration of the silver after we have done the reaction and also did the dissociation of that complex ion. As I said, this other information that we did past that homework assignment 43, this is all concept stuff. You need to be familiar with the concepts for any problems on the test, but I'm not assigning any problems to actually calculate this. I'm more concerned about you learning how to do the acid stuff right now. And make sure you can do those for the test. Okay, but I did want to touch base on this to show you this information.